We will continue with protein denaturation. This is a simple but very useful figure to describe protein denaturation. Denaturation is a process in which proteins lose their shape. So what does that mean? Each protein has its own unique sequence of amino acids, and the interactions between these amino acids create a specific shape. So in this figure, you see that the first one is the native protein in a folded form. The first one is native. And we have denatured protein. So what's the structure of this native protein here? It could be secondary, tertiary, or quaternary structure. It's a three-dimensional folded form. Can it be primary structure? No, it cannot, because primary structure is just the linear sequence of amino acids. It's just a linear random coil. So that's why we cannot talk about losing the shape in that situation. It's not three-dimensional. So the primary structure is already in unfolded form, okay? Therefore, we define protein denaturation as the major changes in the secondary, tertiary, or quaternary structures. Okay. So we are talking about losing shape. So what does shape tell us? So the shape of the protein is important because it determines its function. Remember, proteins can function as a digestive enzyme or a transport protein carrying oxygen in the blood. So in native form, they are functional proteins. They have specific functions. So if the protein is subject to a denaturing agent, so like this, so the internal interactions between the protein's amino acids can be altered, which in turn may alter the shape of the protein. The shape of the protein will change. So if we change the shape, we change the function. So if we lose the shape, so we lose the function arising from the shape. Therefore, denatured protein becomes dysfunctional. Okay. A biologically functional protein is converted to a non-functional form. That's the denaturation. So, what does not change after denaturation? The amino acid sequence does not change. Okay, right here. It's the same. So we have like N terminal here, C here, and amino acids goes like that. It is unfolding, the structure is opening, but the peptide bonds are not broken. So it's unfolding without cleavage of backbone peptide bonds. So is there any bonds broken after denaturation? Yes, denaturation might break disulfide bonds. Disulfide bonds. So remember, disulfide bonds, it's one of the forces stabilizes tertiary structure. So tertiary structure denaturation involves the disruption of disulfide bonds. Okay, if we are talking about tertiary structure, it's possible. Okay, let's continue. So denaturation is a non-spontaneous process. This figure here is the representation of the energy of a protein molecule as a function of its conformation, its shape. The conformation with the lowest energy is usually the native state. The native state is thermodynamically the most stable state with lowest feasible free energy. Any change in conformation away from this native shape will represent an energy cost. So denaturation brings an energy cost. The protein molecule is not completely static. It will flex and bend in response to thermal energy, but will always tend to return to the same shape. When the protein is denatured, the balance of forces acting are changed, and the protein may respond to change shape to minimize its energy under the new conditions. Okay, protein denatures under certain conditions. So is protein denaturation reversible or irreversible? Because the native folded protein is in the lowest energy state, protein denaturation is in principle reversible. Once denaturing condition is removed, the protein will try to get back into its energy minimum, which is the native state. So protein wants to get back to native state to minimize its energy, as mentioned in the previous slide. That's why they can regenerate or refold to their native state, but slowly. It's a slow process, so they can reverse slowly. Okay, let me write here. So denaturation is a fast process. However, regeneration, or we can say refolding, is slow. But in practice, this regeneration, refolding can be difficult because the precise sequence of steps needed to fold the protein is hard to repeat. There is only one native state, but there could be many denatured states like this. So refolding is a complex process, especially for large proteins or complex proteins, complex structures. So there are conditions proteins cannot reverse. Generally, denatured proteins have a greater tendency to aggregate. And aggregated proteins cannot refold. So what happens? So once they aggregate, they may either precipitate or gel. Okay, so protein denaturation can be reversible or irreversible, depending on the denaturing conditions, the amino acid sequence, the structure. Okay, let's continue. Okay, what causes denaturation? During food processing or food preservation, proteins can be exposed to different denaturing agents. They can be physical agents like temperature, hydrostatic pressure, like shear, it's like mixing, blending, or irradiation waves, and also they can be chemical agents like changing the pH, organic solvents, some low molecular weight organic solids, surfactants or salts. So what are the consequences of denaturation? So protein denaturation can result in loss of biological activity. For example, enzyme inactivation, the enzyme won't work after denaturation. It will lose the function, the activity. So another result can be reduced solubility or loss of solubility. For example, like the case in egg protein, milk protein, so they might aggregate after denaturation. Flocculation, precipitation. Precipitation of globular proteins. So when we have reduced solubility or minimum solubility, when a protein is not soluble anymore in solvent or in water, it will precipitate. So, okay, Another result can be improved digestibility. For example, legume proteins. So legume proteins are hard to digest in native state. So when we denature them, we improve the digestibility. So which is desirable. And another result can be improvement of foaming and emulsifying properties. An example can be whipping egg whites. It's an example for improvement of foaming properties. We will see later. The most common way to denature proteins is through heat. When a protein solution is gradually heated above a critical temperature, it undergoes a sharp transition from the native state to the denatured state. And that critical temperature is called denaturation temperature, or in some cases, melting temperature of the proteins. And it depends on the protein type. Here you see some examples. Each protein has different denaturation temperature depending on the amino acid sequence and the structure type. Denaturation temperature is the temperature at the transition midpoint, where the concentration ratio of native and denatured state is 1. Thermal denaturation can be reversible or irreversible depending on the denaturation denaturation temperature and exposure time. By heating a protein, you are going to disrupt a number of different types of interactions. The mechanism of heat-induced denaturation of proteins primarily involves the effect of temperature on the stability of non-covalent interactions. Heating essentially makes the atoms of the polypeptide start to vibrate much more quickly and will break apart interactions. So in this case, the hydrogen bonding and electrostatic interactions, which are exothermic in nature, are destabilized. On the other hand, hydrophobic interactions and they are endothermic. So are stabilized as the temperature increased. Okay. Thermal stability of proteins can be affected by amino acid composition, water content, additives in aqueous solution. So as an example, here in this picture we see eggs. So when eggs are cooked, the egg whites turn from clear to white here, right? And this gel becomes more rubbery. So what is the protein in egg white? It's albumin. So as heat denatured the albumin in the egg white, albumin protein in the egg white, it broke apart some of the bonds, like mostly hydrogen bonds, that were holding the proteins in the original shape. And that process is irreversible. Also, this one is irreversible too. Let's see another way of denaturation. Hydrostatic pressure denaturation. In this picture, you see a high pressure processing equipment which is used to inactivate microorganisms at 2 to 10 kilobar. So under these conditions, some proteins can be denatured. Proteins contain void spaces that can be compressed under high pressure. Void spaces. So what happens? The decrease in volume occurs due to elimination of void spaces. And also hydration of the non-polar amino acid residues. Okay, the decrease in volume occurs due to elimination of void spaces as the protein unfolds, and hydration of the non-polar amino acid residues that become exposed during unfolding. Okay, protein denatures like that under compression. So for many proteins, the denaturation under pressure is highly reversible. When the pressure is relieved, the protein will get back to the native state. No toxic compounds are developed, or there won't be any change on essential amino acid composition, nature, color, and flavor. Globular proteins are more susceptible to that kind of denaturation. Than fibrous proteins. Why? Because globular proteins contain more void spaces. So it's more compressible. Shear denaturation. Several food processing operations involve high shear. High mechanical shear generated by mixing, kneading, whipping, and so forth. And most of the proteins denature and precipitate when they are vigorously agitated. Here you see an example of egg white whipping. In this case, denaturation occurs because of incorporation of air bubbles and adsorption of protein molecules to the air-liquid interface. Proteins are unfolded at the interface. The conformation changes. The extent of conformational change depends on the flexibility of the protein. So highly flexible proteins denature more than rigid proteins. And the rate of shear affects the denaturation. The greater the shear rate, the greater is the degree of denaturation. And this is a highly reversible process. Another denaturing agent is the pH. So when you change the pH, you are going to change the protonation state of the side chains, such as amino groups. Proteins are stable against denaturation at their isoelectric point. When we change the pH, so the net charge of the protein changes. It might be positive or negative, below or above isoelectric point. And this situation can favor protein denaturation because the like charges on the chain repel on another. And this favors expansion of the folded protein structure. Protein becomes unfolded and denatured. So strong intramolecular electrostatic repulsion causes swelling and unfolding of proteins. Degree of unfolding is greater at extreme alkaline pH values because most proteins contain more negatively charged ionizable amino acids. pH-induced denaturation is mostly reversible. In some cases, it can be irreversible if there is an extreme pH, which causes partial hydrolysis, reduction of disulfide bonds, or hydrophobic aggregation. And several small molecular weight solids, such as urea, guanine hydrochloride, detergents, sugars, and natural salts affect protein solubility in aqueous solutions. Generally, sugar alcohols, and free amino acids tend to stabilize the native protein structure. They increase the protein's stability in aqueous solutions. Urea and guanine hydrochloride decrease protein stability by disrupting the hydrogen-bonded structure of water. This makes water a better solvent for nonpolar residues. Another denaturing agent is detergent. SDS, sodium dodecyl sulfate, is a good example of a detergent that causes protein denaturation. Detergents generally bind to the unfolded protein, shifting equilibrium to the unfolded state. Okay, I'm going to stop here. Let me know if you have any questions.